Hi, this is John Whitaker for the Probability 1 class, and this is our fourth video lecture. And last time we ended talking about what it meant for two events to be independent. And what I want to do to start off this lecture is talk about what do we talk about if we have more than two events? What does it mean for them to be independent? And so we're extending that definition of independent events. So here's our definition. It says the events e sub 1, e sub 2, up to e sub n are independent if for any sub-collection let's say e sub 1 prime, e sub 2 prime, e sub r prime of the original collection of events. And the probability of e sub 1 prime intersect e sub 2 prime intersect all the way up to the intersection of e sub r prime is equal to the probability of e sub 1 prime times the probability of e sub 2 prime times the probability of e sub r prime. And what I want to do next is to look at an example of something where they are not independent. Okay. So as an example, it says, let a ball be drawn. This is from our text. Let a ball be drawn from an urn containing 4 balls numbered 1, 2, 3, and 4. So here's our event. We're going to let so 2 balls will be drawn let's not say 2 balls. Let's say let a ball be drawn at random. Okay, and so we're going to find E to be the event that you either got the ball number 1 or 2. We're going to let F be the event that you got the ball number 1 or 3. And G be the event that you got the ball number 1 or 4. Okay. So if you look at the probability of E intersect F, that would be the same thing as the probability that you selected the ball number 1, because that's all that's in common here between these two events. And the chance of that is 1/4. Likewise, the probability of E intersect G, that's going to be the probability that you drew the ball with the 1 on it, and that's equal to 1/4. if you look at the probability of F intersect G, that's going to be equal to the probability that the one ball was drawn, which is equal to 1/4. Now, the probability of E is equal to 1/2. The probability of F is also equal to 1/2. And the probability of G is equal to 1/2. And so so E and F are independent events. E and G are independent events, and F and G are independent events. But let me write that down. I will wait about that. But if you look at the probability of E intersect F intersect G, what that's equal to is equal to the probability that you got the one ball, which is equal to 1/4, which is not equal to the probability of E times the probability of F times the probability of G, which is equal to 1/2 times 1/2 times 1/2, 1/8. So E, F, and G are not independent events. But they are pairwise independent. So any two of the events, the probability of their intersection is equal to the probability of each event times each other. But they're not, as a collection, independent, because the probability of the intersection of all three of them is not equal to the probability of each one of them multiplied together. So just wanted to show that example. And again, it is from the text. That fairly well concludes what I wanted to say out of chapter 1. What I want to do next is move into chapter 2 material. And chapter 2 deals with random variables. So what is a random variable? So as a definition, this is chapter 2. And as a definition, a random variable is a set function which associates each outcome from a random experiment in numbers, real number. And so as an example, let's say a coin is tossed. And so our sample space, our outcomes, are heads, tails. And so what we'll do is we'll define the random variable. So x of h being equal to 1 and x of t being equal to 0 defines a random variable x. That's a random variable. We'll do one more example. So as another example, suppose a person will arrive at a bus stop between 5 p.m. and 5:30 p.m. Let X be the amount of time after 5 p.m. that the person arrives, that the person at the bus stop. Then X is a random variable. Okay, they're kind of different random variables, these two examples that I have listed. One of them only has a finite number of answers. As a matter of fact, it has a countable number of answers. Where this random variable, which takes the time that the person shows up and yields a number, or the amount of time after 5 o'clock that the person showed up. This is uncountable output values, and thus is a different type of random variable. And it'll be called a continuous random variable, whereas the one whose output values only have at most countable outputs, that's going to be called a discrete. We'll go over that in a little bit more detail. What I mean by this situation is that if the person shows up at 15.3 minutes, okay, whatever that is, then X of that time is 15.3 minutes. Okay? And so there are infinitely many, or uncountably many answers for this output values of this X. We're going to begin by talking about the types of random variables that only have at most countable number of output values. And those are called discrete random variables. Let me write that up. So as a definition, a discrete random variable is a random variable that has at most countable number of output values. And so what I'm going to be meaning by countable is meaning that they have the same number of output values as the set of natural numbers. And so to be at most that could be finite, or if it's infinite, it has the same number of output values as the set of natural numbers. That's what I'm going to mean by it. And as an example, if we have a card is drawn from a standard deck we can define x of a heart equaling to -1, x of a black card being equal to 3, and x of a diamond equal to 2. Then this x is a discrete random variable. Let me do one more example. Okay, there's another example. If x counts the number of potholes in a 1-mile section on a certain street, then x is a discrete random variable. That might have infinite number of answers. There might be infinite number of potholes in some sense. Okay. So those are examples. Let us talk about something associated with the discrete random variable. And so what we want to do here is we want to kind of put ourselves in a position where we can relate the chance of something happening to functions, to mathematics that we have some theory about. And so, as a definition, associated to a discrete random variable x is a probability mass function and it's called f of little x, okay, given by f of little x is equal to the probability that the random variable is equal to little x. And we can consider this probability mass function to be defined over the whole real line, okay? But a lot of times, most times, it's going to be defined to be 0 because there's only countable many number of output values for x. Okay. So here, there are some facts about probability mass function. If f of x is a probability mass function, which we'll abbreviate PMF, for a discrete random variable x, Then, here's two facts that we have. First of all, f of x has got to be between 0 and 1. And second of all, if you sum up over all x values such that f of x is greater than 0, you sum up those f of x values, you'll get 1. And that's a true statement, but we could write this down a little bit different. We could say, here, if we have x of i's, we'll sum up over the, I running from 1 to infinity of x of i's. That's going to be equal to 1. What we understand as the x of i's is those are output values for the random variable x. Here, I'll just say as I runs from 1 to whatever it runs to. Okay, that's a nice way of putting it. All right, let's look at our example. Yes. So let's look back at the card example. So a card is selected from standard deck, and we'll refer to this example several times throughout this lecture. Define x of a black card to be 3, x of a heart to be equal to 1, minus 1, I should say. And x of a diamond to be 2. Okay. So here, here's what we're thinking. Then, the PMF for x is, so here's the way I define it. I'd say it's a piecewise defined function. F of x is going to be equal to, well, remember the way that it's defined, f of x is defined to be the probability that big X is equal to that little x. And so here I'm going to say that it's 1/2 if x is equal to 3. So the output values that we have listed here for x are 3, minus 1, and 2. To get a 3, for the output value for x, you had to have drawn a black card. What's the chance that we drew a black card? Well, there are 26 black cards out of the deck of 52, so 26 out of 52, that's 1/2. Here, if x is equal to minus 1, well, let's say 2. That means for x to be equal to 2, you had to get a diamond. The chance of getting a diamond is 1/4. So that's what f of x had to be. It has to be equal to 1/4 if x is equal to minus 1, and it's 0 otherwise. So here as I defined the sum of the f of x of i's from I running from whatever the output values starting at 1 up to how many every output values we have. We sum those up, we're supposed to get 1. Here's what you should note. So the sum, I think I have room to write this here, as I runs from 1 to 3 of f of x of I. In this case, what we're having is f of, I'll write it down this way, is the sum is what are the output values for x? Well, they're x being equal to -1, 2, or 3 of f of x. That's what we mean by our previous notation. And what that is, it's f of -1 plus f of 2 plus f of 3. And lastly, I think I have room to write that down. F of -1, that was 1/4. F of 2, that was 1/4. I'm looking to my left here. And f of 3 was 1/2. And sure enough, that adds up to 1, which is what the sum should be equal to. That adds up to 1. Okay. So that's an example of a probability mass function for a discrete random variable. Okay, the next type of function that I want to look at, definition, is for a random variable. It doesn't have to be discrete. Let's call the random variable x. There exists a function I'm going to call it big F of little x. Let's call it A. Called the cumulative distribution function. Cumulative distribution function of or 4x given by, so here's the way that it's defined. So f of A is equal to the probability that x is less than or equal to A. Okay, we generally denote the cumulative distribution function by the CDF. And here's facts. We'll say let f of x be the CDF for a random variable x. Then so here's the first thing I want to tell you. In some sense, if you will, f of minus infinity, that's going to be equal to 0. So if you take the limit as a goes to minus infinity, you're going to get 0. And f of infinity, that's going to be equal to 1. 2, f is non-decreasing, never goes down. Let me get some more. The third characteristic is that f is right continuous. I'll explain that a little bit more. And a fourth property is the probability that A is less than X is less than or equal to B is equal to f of B minus f of A. All right. I'll list one more fact. I'll put it kind of as a comment more than a fact. But the amount of junk in a CDF at the value A indicates or is the probability that X is equal to A. All right, to get a better understanding of this CDF, let's look at an example. Let's look at the example we had. A card is selected. At random from a standard deck. Define X of a black card is equal to 3. X of a heart is equal to -1. And then X of a diamond, that was equal to 2. Now let's draw the CDF up. Then, the cumulative distribution function of X, we're going to denote it by f of little a. So, what's that equal to? That's equal to the probability that X is less than or equal to A, is, I'm going to draw it graphically. Okay, so let's think about all the possibilities A could be. Well, A could be -17. What's the chance that X is less than or equal to -17? Well, when you think about the output values for X, they were -1, 2, or 3. And so the chance that you got something that was less than or equal to -17, that's 0. So if you think of -17 being way over here, the CDF is going to be 0 up to that point. As a matter of fact, it's going to be 0 all the way up to -1. But at -1, the chance that X is less than or equal to -1 really meant in this situation that X had to be 1, or -1. And the probability that X was equal to -1, well, that means that you got a heart, and that's 1/4. So here we get an output value of 1/4, closed dot there. This is open dot here. And then if you said, well, what's the chance, what's F of, big F of 0? Would that be the probability that X is less than or equal to 0? When you think about the output values for X, they were 3, 2, and -1. So the chances that the output value for X was less than 0 means it's the chance that the output value was equal to -1, and that's still 1/4. So it's 0 up to, where it's going to change is when we get to 2. So it's 1/4. Up to 2. This is 1/4. And then at 2, if we say what's the chance, the probability that X is less than or equal to 2, well, that means that the output value for X was either a 2 or it was -1. That's the possible output values we could get. And so the chance that that happens, so they are mutually exclusive events, because you either had to get a heart or a diamond, well, that's half the time. So we should be up at 1/2 at that point. And that's what it should remain until 3. And then after 3, you say, what's the probability X is less than or equal to 3? Well, that means that X was either -1 or 2 or 3. That's all the output values we could have gotten for X. So that's 100% or 1. And it's going to be 1 from the rest of the way. You say, what's the chance, if you had A is equal to 17, what's the chance that X is less than or equal to 17? Well, the output values for X are 3, 2, or -1. So all the time, it's 100% that the output values are going to be less than 17. So that's why we get 1. Put that 1 better. Okay, you can see that this function, if you go to the far left, is 0, to the far right, it's 1. You can also see that it is non-decreasing. It stays the same, okay? But it never goes down, okay? So it's non-decreasing. You can also see that it's right continuous. Okay? What I mean by that is that if you come in from the right, let's say -1, that the limit as you come in from the right of -1 equals to f of -1. So it's continuous in that way. Also, just let me say something about one more fact. You notice that the jump, so the jump here at 2 from where you were to the left of 2 to where you are at the right. So the jump of 2 is 1/4. It's a difference of 1/4 from 1/2 to 1/4. And that is the probability that x is equal to 2, or the probability that you got a diamond. Okay? Just like here, the jump at 3 is 1/2, and that was the way that you got a 3 was that you had to have a black card, and the chance of getting the black card is 1/2. That's what I need to say. The next thing that I want to talk about is a definition about the expected value of a discrete random variable. So the expected value or mean, really that means average, of a discrete random variable x is denoted by e of x and given by so I don't have that room. Is given by e of x is equal to the sum over all x values such that f of x is greater than 0 of x times f of x, where f of x is the probability mass function of x. Let's look at an example. So let's go back to that card example. Card is selected at random. We have x of the black card is equal to 3. X of a heart was equal to -1. X of a diamond was equal to 2. Find the expected value of x. Well, here's the answer. The expected value of x is going to be the sum of the output values. So this is x going to be equal to -1, 2, 3 of x times f of x. And so that's going to be equal to -1 times f of -1. It's going to be plus, that's what sum means, 2 times f of 2 plus 3 times f of 3. So that's what we have. And so numerically what this is, it's -1, and f of -1, that was going to be equal to 1/4, plus 2, and f of 2 was 1/4, plus 3, and f of 3 was 1/2. And so, let's see, this ends up being 1/4, so it's a -1/4 plus 2/4, that's 1/4. plus, this is 3/2, or if you will, 6/4, and so we end up getting 7/4. So not quite 2. Okay. Now you can notice that this expected value, x being equal to 7/4, we never can get 7/4 as one of our answers for an output value for this random variable, but that's on average what would happen. That's the average value you get. Well, turns out we can kind of generalize this expected value of x, and that's what I want to do next. So as a definition, given a discrete random variable, x, and a function g of x, then the expected value of g of x is equal to, it's the sum over all x values such that f of x is greater than 0, of g of x times f of x, where f of x is the PMF of x, the probability mass function. Let's look at an example of this. We'll go to our card example. Okay, so a card is drawn at random. From a standard deck. Let x of a black card be defined to equal 3, x of a heart be equal to -1, and x of a diamond be equal to 2. Then, or somebody might say, find the expected value of x squared minus 2x. Okay, so my g of x is x squared minus 2x. So the answer is, expected value of x squared minus 2x is equal to the sum over the output values for x. So this again, x equal to -1, 2, 3 of g of x, so that's going to be x squared minus 2x times f of x. So this is going to be equal to, so if I stick in -1, I've got -1 squared, that's 1, plus 2, so I end up getting 3 times f of -1. Plus, when I stick in 2, 2 squared is 4, minus 4, that's 0 times f of 2. Plus, here, when I stick in 3, I'm going to get 9 minus 6, that's 3 times f of 3. And so here, this answer is, it's 3 times, well, f of -1, that was 1/4. And this is going to be 0, this middle term, because it's multiplying by 0. And then here, plus f of 3, 3 times f of 3, well, f of 3 was equal to 1/2. So this ends up being 3/4 plus 3/2, which is 6/4, so we end up getting 9/4 as the expected value of x squared minus 2x. So 9/4. Okay. Well, I want to look at one more item. And that is the variance. So, given a discrete random variable, x, the variance of x is denoted by VAR of x and given by the variance of x is equal to is the expected value of the quantity x minus the expected value of x to be squared. So that's the variance of x. The variance of x gives some kind of indication of the spread of the output values of x. That's what it is. There's a big fact associated with the variance of x, and that's what I'd like to look at next. And we'll end with this big fact. Really, my definition for the variance of x, that's what it's defined to be for any type of random variable, but we're just looking at discrete at this time. Okay, so the big fact we'll look at next is that the variance of x, let me see this one. If x is a discrete random variable, the variance of x is equal to the expected value of x squared minus the expected value of x to b squared. Expected value of x to b squared. Okay? So let's prove this fact. So note the variance of x is defined to be the expected value of the quantity x minus the expected value of x to b squared. Okay? Now the expected value of x is a number. So this is equal to the expected value. If I square this out, what I did is x squared minus 2 times x times the expected value of x, and then plus the expected value of x to b squared. Okay, now this is a sum, so it's the sum over all the output values for x where f of x is greater than 0. Of, it would be x squared minus 2 times x times the expected value of x plus the expected value of x to b squared. All that times f of x, the PMF. Almost done. Okay, that would be equal to a sum over all x values such that f of x is greater than 0 of x squared times f of x plus 2 times x times the expected value of x times f of x plus, I think I have room. Here it would be the expected value of x to b squared times f of x. And so I can break this up into three sums. If the sum over all x values where f of x is greater than 0 of x squared times f of x plus the sum over all x values where f of x such that f of x is greater than 0 of 2 times x times the expected value of x times f of x plus the sum over all x values such that f of x is greater than 0 of expected value of x to b squared times f of x. Now the expected value of x is a constant, but let's worry about this first sum. This first sum, by our definition of the expected value of a function of x, is equal to the expected value of x to b squared. That's what this is. Plus, here the 2 and the expected value of x are constant, so we pull them out of the sum. This is x times f of x, x times f of x. And plus here, this expected value of x squared, expected value of x to b squared is a constant, so I pull this out. And then this is a sum here over all x values such that f of x is greater than 0 of just f of x. Okay. Now, the expected value of x squared, that's what it is. Here, this is 2 times the expected value of x. Now, the sum of all x values times, the sum of the x values times f of x, that's nothing more than the expected value of x. And here, this is plus the expected value of x squared, to b squared, I should say. And the sum of the f of x such that f of x is greater than 0, that's by property of f of x, that's equal to 1. Now, I've made a mistake. My mistake is on this part of the board. And it's from copying from the left part of the board. But there was a subtraction here. So that's what's wrong. So we need to make a correction. Sorry. So that's what it is. Now look, the expected value of x times the expected value of x, that's the expected value of x squared. Here we got one expected value of x. And here we got minus 2. So that means we have a minus the expected value of x to b squared. So the first thing is the expected value of x minus the expected value of x to b squared, and that is the proof. And we'll start off next time by doing an example of where we use, or where we calculate the variance for random variable. We'll probably do the card problem. Thank you very much.